Hey guys. So as I mentioned in class, I would like to have you guys work on some of this on your own at home over the weekend because we really are running very low on time. So anyway, this is page 150 in your workbook. So if you could just make sure you're turned to that, and we'll do the odd problems. So let's take a look at problem number 13. For 13, this is very similar to problem 11 that we did already, in the sense that it has a binomial numerator and a monomial denominator. Right, so we're looking at a binomial numerator, a monomial denominator. So again, we talked about so many different strategies today. I'm really happy with how many ideas you could come up with, but I just have to pick one. So I'm going to pick one that we talked about where we would maybe simplify this first before multiplying numerator and denominator by something to get rid of the radical. All right, so I'm going to choose to simplify this first, so we get 4x cubed minus 3 times the square root of 3x. And then in this, the square root of 3 can't come out, but the x squared can come out. This would become a 3x times square root of 3. Right, again, that's not always going to be the strategy that you choose. I don't always choose that strategy, so I'm just telling you that you can do that. All right, now again, we look for those things that make this considered to be fully simplified, and one of the obvious ones right now is that math faux pas is don't leave a radical in the denominator. All right, so the strategy we talked about in class today was multiplying it by itself. All right, because when I do that, square root of 3 times square root of 3 will lose the radical. The other thing I mentioned in class today is please put parentheses around that so that you remember that you're distributing the square root of 3 to everything. Okay, so then when we do that in the top, well, when I multiply this term, 4x cubed times the square root of 3, I get 4x cubed times the square root of 3. There's no any here to combine it with, so it just kind of gets tacked onto the end. Right, but then in this one, when I multiply this by square root of 3, I get 3, and then again, I'm just going to smush those together underneath, so it's going to be 3x times 3, in other words, 9x. And then in the denominator, I'm going to do square root of 3 times 3x square root of 3. So this square root of 3 times this square root of 3 will turn into a square root of 9, which becomes a 3, and we'll join the outies. So this will become 9x right here. Now, I could have done that in this case too. I could have done it right away, but I'm going to do it in a separate step here. So this is going to become 4x cubed square root of 3, and then this 9 will join the 3 outside as a 3, so then it becomes 3 times 3, which is 9, square root of x over 9x. Right, so let's go through our list of things. So we say, are all the innies simplified? All right, so can I do anything with square root of 3 to make it smaller? Can I break any factor out because it's a perfect square? Hopefully you say no. Same thing with x. All right, I cannot, there is no perfect square in x. If it had an even exponent, if it had an exponent higher than 1, I could do that, but I can't. So that's one thing. The second thing is, and this is the part that I know gets everybody just all riled up, is I have to look at all of the outies, every one of them, and see if they have anything in common. All right, so I would look at all 3 of them, not just one of them, not just 2 of them, all 3 of them. So if I'm looking here, I say, oh, awesome, these 2 have a 9, but 4 doesn't share a common factor with 9. Or I would say, oh, yes, these both have an x, but this doesn't. So I can't cancel anything out of those, even though it's so incredibly tempting to cancel these 9s, to cancel the x's. If it's not common to all of them, it's not going to cancel. And then the same thing, again, you might argue, look, that this has an x in it, but it's an any, and these are all outies. So I can't simplify that. All right, and then the other thing that we looked at is, did I get all the radicals out of the denominator? And the answer is yes. So this, as unsimplified as it looks, is actually the most simplified form that we can get on that. All right, so 4 times x cubed times square root of 3 minus 9 times square root of x all over 9x. All right, now other strategies that you could have used, you could have right from the very beginning multiplied top and bottom times 3 times this, times the square root of 3x squared. In fact, I think that's what I did in the answer key, and it will still get you to this, but it will be more work. Right? If you don't fully simplify that denominator first, you are going to have to cancel. Sometimes you might say, that's fine, I don't mind. Other times you're really going to want to do it. So in this case, I did it. You can see that the other way, when I did not use the most simplified form of that first, to see that it does take longer. But okay, this is the part. We now have 4 remaining problems. We have 15, 17, 19, and 21, and all of them have something new in them, and that is that now the denominator is a binomial. Right, so we have a 4 plus 4 root 5 here. In 17 we have negative 3 minus 3 root 3, and here in number 19 we have negative 4 plus 4 root 2. So all of the denominators switch from being monomials like we had here and in every other problem that we've done so far, to now they are binomials. And I'm not going to lie, these definitely are harder conceptually to understand because the strategy is slightly different. So I'm going to start with the same strategy, which is what everybody would guess you would do if I asked you what do you think you would do. All of you would probably say, let me try multiplying this by square root of 5. This is wrong, so you can just follow along or take notes, but don't write this on your paper because it's not right. So you would say, well, let me multiply by square root of 5 times square root of 5, right? So that's a good guess because that's what worked for us before. But when I do that, again, put parentheses around the binomials. In the numerator, I get 3 root 5. In the denominator, as I distribute this, here, with the 4 root 5 times root 5, the root 5 times root 5 just gives me 5 times that 4 outside, so I get plus 20. So I'm psyched about that. And then I do this. All right, 4 times root 5, and I get 4 root 5. And I realize that all I've done is I've moved the radical from this term to this term. All right, it did not get rid of it. Right, then sometimes people say, well, how about I just multiply it by itself? All right, another good thought, because it would be like squaring. All right, so if I multiply top and bottom just by the whole bottom, right, it doesn't matter what we get in the numerator. There's no faux pas about having a radical in the numerator. This would give me 12 plus 12 root 5. All right, and here it's kind of a pain in the neck, but we're going to have to FOIL it out. So we'll get 4 times 4 is 16. 4 times 4 root 5 is 16 root 5. 4 root 5 times 4 is another 16 root 5. And 4 root 5 times 4 root 5 is that 20 that we got before. And so we get 12 plus 12 root 5 over 16 and 20 is 36, but we still have that root 5 in the denominator. It just doesn't want to leave. All right, so I'm going to tell you what the strategy is. All right, since the two obvious ones, just multiplying by square root of 5 or multiplying it by itself, don't work. So let me get rid of this. All right, so the correct strategy involves us using a new word. Oof. Okay, so here's what we're going to do. I'll tell you how to do it, and then I'll tell you what it's called. All right, so instead of multiplying it by itself, instead of multiplying just by root 5, here's what we're going to do. We're going to keep the 4 the same. We're going to keep the 4 root 5 the same, but we're going to change the signs. All right, so just that middle term or that middle sign is going to change from, if it's positive, it changes to negative. If it's negative, it changes to positive. But it is going to change to the opposite sign. Now this might remind you of difference of squares factoring, where we had some number plus this and then some number minus the same thing. And that is exactly what we're taking advantage of, is the canceling that happens in difference of squares factoring. So we're still going to do 4 minus 4 root 5 up top. All right, so again, this is the only difference, is that it's got that minus sign in between instead of the plus. All right, so now let's multiply that out. So if I do 3 times 4 minus 4 root 5, I get 12 minus 12 root 5. All right, just distributing that in. And then in the denominator, all right, this is going to take up some space here, but we can do it. 4 times 4, 16. Then we do the outer ones. 4 times negative 4 root 5 is negative 16 root 5. All right, here's where the beautiful things happen. Now we multiply 4 root 5 times positive 4, and we get plus 16 root 5. And then 4 root 5 times negative 4 root 5. Right, that's going to give us negative 16 times 5. Oh, I think I made a mistake before when I said that. It's going to give us, I just said it was 20. It wasn't really 20. That's going to give us 16 times root 5 times root 5, which is just 5. So this is going to give us 16 times 5, which is 80. Yeah, I'm positive I said 20 before, so ignore that error that I made there. It should have been 80. All right, so here's the nice thing, is that when I choose opposite signs here, these two middle terms are always going to cancel out. All right, so we're just going to be left with the product of the first two, the 4 times 4, and the product of the last two, which was 16 times 5, or 80. All right, so let's clean this up then. So we've got 12 minus 12 root 5, and then we've got 16 minus 80, which is 64, negative. All right, so then we have gotten rid of that radical in the denominator. All right, so let's go through some of our things. One is, did we get all the radicals of the denominator? Yes. The second thing is, are all remaining radicals simplified? Yes, there's nothing I can do with square root of 5. Third thing is, can I simplify all the outies? So we've got this 12, and this 64, and we're looking for some common factor that they share. So do you see a common factor that they share? Hopefully you would say 4, right? I'm going to go even further, and I'm going to say negative 4, just to get that negative out of the denominator. So I'm going to divide every one of these three outies by negative 4. So that's going to change this 12 to a negative 3. It's going to change this negative 12 to a positive 3. And it's going to change this negative 64 to a positive 16. All right, final answer right there. All right, is that we have no radicals in the denominator. We've simplified all the outies, found common factors in all of them, and then we've made sure that our radicals are completely simplified. Okay, let's take a look at problem number 17. Okay, so for problem 17, same idea, and that is when we have a binomial in the denominator and one of them or both of them contains a radical, that what we need to do is multiply top and bottom by the same numbers. So it's going to be minus 3 and 3 root 3, but we're going to change that middle sign, just the middle sign. Don't change the first sign and the second sign. Don't change just the first sign, but not the second sign. Just change the middle sign. Just change the middle sign. All right, so that's going to be negative 3 plus 3 root 3. And I'm going to do the same thing up top. Negative 3 plus 3 root 3. Put parentheses around your binomials to remember that you're either distributing or doing FOIL. Okay, so let's distribute the top. That's the easy part. All right, so we get 5 times negative 3, negative 15. 5 times 3 root 3 becomes plus 15 root 3. In the denominator here, I'm going to do negative 3 times negative 3 is positive 9. I'm going to do negative 3 times positive 3 root 3, which is going to give me negative 9 root 3. I'm going to do negative 3 root 3 times negative 3, which is going to give me positive 9 root 3. And negative 3 root 3 times positive 3 root 3. The 3's on the outside will become a 9. And then the root 3 times root 3 becomes 3. So I'm going to have 9 on the outside, and I'm going to join it with another 3. So it's going to be minus 27. All right, so again, first give that, the outers give this one, the inners give this one, and the lasts gives us minus 27. And again, just like in the last problem, those middle two terms will always cancel out if you choose this method right here. If you leave the first term alone, leave the last term alone, but then just change the sign between them. All right. So in the numerator, we've got negative 15 plus 15 root 3. And then in the denominator, we've got 9 minus 27, which is going to give us negative 18. All right, we've removed the radicals from the denominator, or singular radical. This cannot be simplified any further. That's the second thing. The third thing is check all three of your outies, okay? And so I've got this negative 15, this positive 15, and this negative 18. Again, don't even look at this because outies and innies don't mix. All right, so we've got these three things right here, and I see that they all have a 3 in common. In fact, I'm going to go with a negative 3 so that I lose that negative in the denominator. So I'm going to go through and divide each of these things by negative 3. So when I take negative 15 and divide by negative 3, I get positive 5. When I take positive 15 and I divide it by negative 3, I get negative 5. Square root of 3. And then when I divide negative 18 by negative 3, I get positive 6. All right, final answer. Okay, now number 19 can look a little bit scarier because now we have the binomial in the denominator and a binomial in the numerator. Again, I'm not going to lie to you, they do get to be more cumbersome, but the strategy is still the same. Again, we're concerned about that radical in the denominator. That's the problem right here. All right, so think about, based on what we did in the last two problems, what would you multiply top and bottom by? All right, hopefully you said negative 4 minus 4 root 2. Negative 4 minus 4 root 2. All right, again, the negative 4 stays the same. The 4 root 2 stays the same. It's just that sign in the middle that changes. Put parentheses around all your binomials so that you remember that you are doing FOIL or distributing. All right, let's look at the top. All right, so 2 times negative 4, negative 8. 2 times negative 4 root 2 is going to be negative 8 root 2. Again, remember, outies times outies, innies times innies. Okay, and then that was this pair. Then we'll do negative 4 times 5 root 3. That's going to give us negative 20 root 3. And then 5 root 3 times negative 4 root 2. So the 5 times the negative 4 is going to give us negative 20. And then under the radical, we're going to get 6. Over negative 4 times negative 4, positive 16. Negative 4 times negative 4 root 2 is going to become a positive, and it's going to be a 16 root 2. Then we do the inside ones. So we did firsts, outers, now inners. 4 root 2 times negative 4 is going to give us negative 16 root 2. And then lasts is going to be positive 4 root 2 times negative 4 root 2. The positive 4 times the negative 4 is going to give me negative 16. And then the root 2 times root 2 is just going to be 2. So actually this should be a 32. And again, we can cancel these. So in the denominator, we end up with a denominator of negative 16. Now, unfortunately, none of these can combine, right? None of them are like terms because the only way we can add or subtract radicals is if all of their radicals are the same. All right, so this has no radical, it can't add with any of these. This has a radical of 2, but none of the other ones do. Same thing with this one and this one. So this is just going to end up being negative 16 in the denominator, negative 8 minus 8 root 2 minus 20 root 3 minus 20 root 6 all over negative 16. I'm going to scooch that negative 16 over so it's more centrally located. All right, last step is we're going to go through and we're going to say, let's look at all the outies, right? The negative 8, the negative 8, the negative 20, the negative 20, and the negative 16. Do they all have a factor in common? Yep, they have a negative 4. All right, so let's divide every single one of these by negative 4. So negative 8 divided by negative 4 is positive 2. Negative 8 divided by negative 4 is also a positive 2, but now we also have the root 2 with it. Negative 20 divided by negative 4 is positive 5, and we still have the root 3. Negative 20 divided by negative 4 is also positive 5, but now it's 5 root 6. And then negative 16 divided by negative 4 is positive 4. Final answer. All right, none of our radicals can be simplified. There's no radical left in the denominator. There's no like terms that we can combine. And we've found all the common factors in all of our outies. Okay, last one is going to be 21. Okay. This actual one is, I think, a little bit nicer than the last one. The last one was problematic because we had coefficients with both our numerator and denominator in front of our radicals. Second, they were different radicals, root 3 and root 2. Here, we don't have those kind of coefficients in front of the radicals, and we also just have the same root 5. All right, so even though it's a binomial over a binomial, it should be a little bit neater than this one was. Okay, I'm going to write it down here because I'm getting a little too close. So square root of 5 plus 3 over 4 minus square root of 5. All right, actually, how about you pause and do this one on your own? All right, I think you can do it based on the last two that we did. So pause the video and go through and do this, and then turn it back on, and then I'll work through it so that you can just double check your work. Okay, turn it off. Okay, so for this one, you're going to do 4 plus root 5, 4 plus root 5. Put those parentheses around, please. You don't want to accidentally multiply just parts of things that you're supposed to multiply. Okay, so when we do that, we're going to get in the numerator root 5 times 4, which is just 4 root 5. And then we'll do the outers. So root 5 times root 5 is square root of 25, which is 5. And then inside here we get 4 times 3, which is 12. And then 3 times root 5 is 3 root 5. And then in the denominator, we get 4 times 4 is 16. 4 times positive root 5 is plus 4 root 5. Negative root 5 times 4 is negative 4 root 5. And negative root 5 times positive root 5 is negative 5. All right, as always, these cancel out. All right. In the numerator, we've got 4 root 5 plus 3 root 5. Again, because our radicals are identical, we can add them together. So 4 root 5 plus 3 root 5 is 7 root 5. And then 5 plus 12 is plus 17. And in the denominator, we've got 16 minus 5, which is 11. All right, so let's go through our list again. I keep saying them in different orders, and I'm sorry about that. I just think of what ones I think of. First of all, we got the radical out of the denominator. Second of all, any remaining radicals are fully simplified. I can't do anything with that root 5. Third is I look at all my outies and I say, can I find any common factor in them? And the answer is no, they're all primes, right? So they have no common factor except 1, which isn't going to simplify anything. So that is our final answer. Right, much easier than problem number 19 was. All right, so as you go through and do these, I think that you're going to run into, from an algebraic perspective, none of the ones that are on this side are particularly easy, but they still use the same strategies. So just maybe you might want to do 20 and 22 on a separate piece of paper just to make sure that you have enough room to do that. Because again, notice that here we do have 2 same radicals, but then there's a different one. Same thing here. Actually, no same radicals. They're all different. Here, no same radicals. So you'll just maybe need a little bit more paper for this side. Okay, let me know if you have any questions. We'll talk more about them on Tuesday. Bye.